Yes, indeed. And this is joint work with Jonas and Robbert, who are both here. Okay, so our goal today is to make a separation logic for message passing, where you get deadlock freedom for free. And in particular, what we want is that for all programs E, if we prove this trivial Hort triple, then E, when we run it, does not deadlock. Okay, so there are two important pieces of previous work, and that is Actris and Iris, which is an existing separation logic for message passing, and linear session types, which give deadlock freedom for free. And in this work, we combine those two. So what are linear session types? Well, linear session types are sort of protocol-based types for channels. So here C is a channel, and this syntax tells you that on this channel you first need to send an int, then you can receive a bool, and then you end. And there are tons of extensions of this, with recursion and many other features. But the interesting thing here is that due to the linear type checking, you automatically get deadlock freedom for your programs. And there are no extra proof obligations like lock orders or some kind of well-founded properties or things like that. Okay, so session types are a type system, and those are nice, but they usually give you some kind of standard safety property, whereas with program logics you can prove functional correctness as well. On the other hand, type systems give you automatic checking, whereas program logics require manual proof. And an important difference here is that in type systems, ownership is usually tied to values. There is no distinction, whereas in separation logic, those two are separate. So let me first talk a little bit about Iris, which Actris is built on. So Iris starts with coq. Iris is built on that. So the first component of Iris is heap lang, which is the E in the Hort triple. And this Iris likes to construct programs as abstract syntax trees in coq. Then the P and Q in the Hort triple, those are called iprops in Iris, and Iris has some very expressive logic for constructing those. Thirdly, we have the Hort triples themselves, which we can state as lemmas in coq. And lastly, we have the Iris proof mode, which lets us prove those Hort triples. And then on top of this, Jonas and his collaborators built Actris. And this is an extension of Iris with message passing. And in Actris, you consider programs like this. So we first here create a new channel. Then in the forked off thread, we receive a message, incremented by 1, and send it back. In the main thread, we send the message 2. We receive a message, and then we assert that this is 3. And as you can see, the fact that this is 3 requires the other thread to do the right thing. Okay, so in Actris we have something similar to session types, but extended to be more powerful. So in Actris you have these kind of protocols which here say that you have to send a natural number. From C you receive a natural number, and then you send the number that is 1 greater. Actris can also interact with mutable state. Here's an example of that. So here we create a channel, a reference, and then the forked off thread will first receive from the channel, increment the reference by that amount, and then send 1 back. The other thread will send the message 2, receive from the other thread, and increment the reference again. And the fact that this at the end produces 3 relies on the synchronization provided by the message passing. And that's why Actris allows you to put separation logic resources in your protocols to be transferred when you send a message. So the problem that we want to solve here is that Actris is not sensitive to deadlocks. So consider our example. If we remove the fork, Actris doesn't care, so you can still prove the same Hort triple as before. But as you can see now, we receive a message immediately after creating the channel. So the other party is never going to send because that other party is us. You can also have more complicated forms of deadlock, such as on the right. Here we create 2 channels, and both threads do send a message on that channel, but they first receive, so that is also never going to happen. So this raises the question, okay, what does a Hort triple in Actris actually mean? And for that we have to look into Iris's adequacy theorem. And Iris's adequacy theorem says if you prove such a trivial Hall triple, then no thread gets stuck, and this is what we call safety. But this is partial correctness, so E is allowed to loop. And if you look into how Actris implements receive, I don't know if it's still true, but originally that was based on a lock, and the lock is a spin loop. So if you write such a deadlock, then this spin loop will be infinite. And this is fine, because it's partial correctness. But in this work, we want to distinguish other loops from being stuck in such a spin loop. So that's our contribution. We want to rule out deadlocking programs such as on the left, while still allowing programs such as on the right. So to do this, we first need a way to state the theorem. And what we decided to do is to make receive a primitive operation, which gets stuck in the operational semantics. And then we have two adequacy theorems. The first one is safety, which is similar to the one that Actris has, which says that no thread gets stuck except on receive. In addition, we have a global progress theorem, which says that the configuration as a whole never gets stuck. And actually, we also have a third one, which is actually combined with the second one, and that is that no memory is ever leaked. Okay, to do this, we actually only need to make a few surgical changes to the Actris proof rules. The first change is to make the logic linear. So Iris is affine. Here we need the logic to be linear. And the reason is that otherwise we could drop these kind of send obligations. And if you're not going to send, then the other side might get stuck if they are trying to receive. The second change is that we need to combine new channel with fork. So it's important here that the two channel endpoints end up in different threads. And that's why we combine the creation of channels, the creation of threads, with a channel used to communicate with that thread. And the third change, which we are very sad about, is that we need to remove iris invariance. So this is very unfortunate, future work. But the thing is, if you do this, then the existing Actris proof rules, well, a little bit changed, already guarantee deadlock freedom. So let's look at that. What goes wrong if we try to verify our deadlocking program? Well, the thing here is we only have fork chance, so we cannot even obtain a channel without doing the fork. So this program, if you delete the fork, it's not going to work. We could try to be clever and use fork chan and somehow try to smuggle this channel out of the fork. For example, here we create a reference, and inside the forked off thread, we try to smuggle this channel out via the reference. But this doesn't work. You can also see it's erased, I think. We could try to send the endpoint back via the channel itself. Turns out that this also doesn't work, because now we are using the channel twice somehow. And that doesn't work. So escape attempts do not work. And this is indeed the key challenge. How do we prove that no escape attempt works? Because we don't want to rule out putting channels in references or sending channels as messages wholesale. We only want to rule it out when, well, as much as possible, we want to still allow it if it's safe. For example, here, this is fine. We have a reference, and then eventually the main thread will set that reference to a channel endpoint. The first forked off thread will receive a number from its D1 channel, and then dereference this reference, which then contains a channel by that point, and send a message back, and then in the other thread it's received and we assert that it's true. So this program is fine, and we can prove that this works. So what does the adequacy proof look like? Well, I cannot describe it in detail, but one difference is that in Iris there is somehow one shared resource world for all threads. In LinearActris this is different because there is a separate separation logic world per thread and channel, and they are connected by the ownership. So if a thread holds ownership, an ownership assertion for a channel, they are connected in this graph. In particular, if we have two ownership assertions for the same channel in one thread, inside our logic we can prove that this entails false. but those ownership assertions can still exist in separate threads. That's fine. And the invariant on this graph is that it is, in some sense, acyclic. In addition, to support higher order protocols, which means that we send channels over channels, and to support infinite protocols, our model here is based on step indexing, like Iris. But for the details, you have to look at the paper. So the architecture of LinearActris is very similar to Iris. So we start with Coq. We have our channelling, which has primitive channels and mutable references. We have Actris-style session protocols, which support various features. We have our propositions for the Horde triples without invariance. We have the Horde triples themselves, which we can state as lemmas, and we use the Iris proof mode to prove these Horde triples correct. Finally, we have our two adequacy theorems. Okay, let's look at an example. This was an example already in Actris, and that is Actris merge sort. So in Actris merge sort, we don't use lists, but we use channels. So we send a bunch of numbers on a channel, and then at some point we say, okay, now sort. And then we receive them back, but in sorted order. And this is all done concurrently by somehow spawning channels and threads that handle half of the list. So as you can imagine, this creates a big concurrent mess, but due to LinearActris, the deadlock freedom comes for free here. There are no additional proof obligations. The original proof of Actris basically just worked. Another question is, can we verify every session type program? And the answer is yes. We have a semantic type system for channeling. And this type system supports mutable references, polymorphism, recursion, and so on. And then we follow the usual Iris recipe for semantic typing. And this then gives us deadlock freedom for session types. Okay, this was my talk. So future work, we would like other concurrency primitives, not just message passing. Of course, ideally, we want some form of Iris invariance. Unfortunately, if you just add the rules of Iris invariance to the logic, then it's very easy to create deadlocks. So we need to change the rules somehow. And another direction for future work is to have liveness, because we here still have partial correctness, which is kind of nice if you want to do a semantic type system, because most realistic languages, they do support loops, and you do not want necessarily to prove termination for all your loops. But it would still be interesting to have a stronger adequacy theorem that is able to guarantee liveness. But this is all future work. Okay, that's it.
Great. So, questions in the back?
Hi, this is really nice work. So I had a question about your APROP. So did you need to not use Iris and just build your own separation model logic model in order to make it linear, or is it? Yeah. Are you reusing any of Iris?
We are reusing SBI, but Iris is not yet based on SBI. So in the future, we are reusing something from future Iris.
Sorry. What's SBI?
This is so currently in Iris it's step indexed and it has resources, but this is built in one step. In the future, this will be refactored to first build a step indexed logic without resources, and then build the resources on top of it. We are doing that here.
Okay, thanks.
So you mentioned that the proofs that you were doing in many cases were very easy. It's over here. Yeah. They were very easy. It makes me wonder, could you take the ideas here and be more automatic? So build an automatic program analyzer which analyzes very big programs and either proves deadlock freedom or disproves it. If your proofs are very simple, and I'm reminded of a work by Jonas and Sergi and some people from Meta who did a POPL paper on disproving deadlock, right? And so I'm just asking, would you speculate about that?
Yes, I think this is possible because I think Ike who made diaphragm, already did some experiments for automating actress proofs, and I think that automation should just work here. I don't think there's any additional difficulty unless diaphragm somehow essentially relies on the iris being affine, but I would suspect it does not.
So just to be clear, I mean, the input would be a bare program with no spec, and the output would be yes, no, deadlock. Do you think you can do that? I think you can, by the way.
I think with diaphragm you would still need to have the protocols for the channels. You would need to give those. I think the rest would be automated. But perhaps I can figure out how to automatically find the protocols.
Thank you for the great talk. May I ask a question? So is this 6 question over? Yeah. So does this work or any other work in the literature try to prove some form of like the completeness theorem that like a reasonably large set of Deadlock-Free program can be proven within the system? Or do you have any comment or speculation in this regard?
I'm not sure I completely understand the question. Do you mean coupling as in probabilistic programming, or?
No, not the probabilistic programming, but any Deadlock-Free program can be proven within this system. Completeness.
Completeness.
Not the soundness, but the other.
Well, I think it's definitely not complete.
Yep.
We know examples that we cannot prove deadlock-free, that are nevertheless deadlock-free. So I think there are two reasoning principles for deadlock-free, two main reasoning principles. One reasoning principle is the kind of session type thing, which relies on somehow an acyclicity of a graph that's maintained. You also have reasoning based on somehow log orders, but you can do something like that for message passing as well. And they are incomparable in strength, I think. So perhaps we can combine them to get a stronger logic, but this logic is definitely not complete for deadlock freedom.
Thank you.
More questions?
Yeah, I was wondering if you could please, maybe it's a very complicated problem, but could you speak briefly about what it would look like to get some kind of invariance back into the system? So presumably you're not allowed to put channels in invariance and then forget about them. This is a problem. So
this is a problem. So I think you would need invariance to be linear, but of course those would be fairly useless. So what you could do is, I think, when you fork, that you would be able to duplicate an invariant at that point, but only one invariant. I think it would look something like that, but it's not very clear what it would actually look like.
thank you.
Actually, I was wondering about that. Could you use cancelable invariants?
Perhaps. I think you would want them to be cancelable, because if your invariants are linear, then it's a problem if they are not cancelable.
There's an online question. There's a tension between guaranteeing deadlock freedom and allowing users to write the programs they want to write. How did you evaluate that second aspect?
Well, I do not really know which programs people want to write, but the programs that Jonas wrote as examples for Actris, well, for example, this merge sort, that just worked. So, well, I have not done a study of what kind of programs people actually want to write, so that I don't know.
Basically, assuming session types are useful, we go beyond that.
Yeah, that's true. So.
Right, thanks. We have time for one more question if anyone has one.
Yeah, nice work. I wanted to ask, if you don't have invariants, how do you build the semantic typing model of references?
So yeah, in the type system, these references are fairly useless in a way, because they are just linear references. Because if you have nonlinear references, then you can easily create a deadlock by putting a channel in your reference and then dropping it.
All right,
So
thanks.
the theorem would be false if you allowed that.
Right, let's thank the speaker again.